Good day, everyone. I remain Engineer Shegun, and you're welcome back to re-class. Today, we'll be talking about simple machines. Now, according to the word simple machines, it means we are looking at those very simple appliances, simple devices that we can see around us. A simple machine is basically a device that allows work to be done much easily. This is just a layman's definition. However, in physics, a machine or a simple machine is a device that allows effort to be applied at one point in order to overcome a load at another point. That is a simple machine. A simple machine. Now, examples of simple machines will include your scissors, will include your plier, will include your lever, will include your pulley, your screw jack, and your wheel and axle. All of these are simple machines. Before we go down into simple machine, there are some terms that we should look at when it comes to simple machine. And one of that term is mechanical advantage. What do we mean by mechanical advantage? Mechanical advantage is the ability of a machine to overcome a load by the application of a relatively small effort. That is the comprehensive definition for mechanical advantage. Mathematically, mechanical advantage is a ratio of load to effort. That is mechanical advantage, a ratio of load to effort. Because load is a force and effort is a force, mechanical advantage is also called force ratio. So therefore, the first important formula in machines is that mechanical advantage, MA, is equals to load divided by the effort applied. Now, what will be the unit if I ask? The unit of mechanical advantage, in fact, there's no unit for mechanical advantage. Why is that so? Because load is in Newton and effort is in Newton, so they will cancel out. This is mechanical advantage. The next term that we need to understand is velocity ratio. As the name implies, velocity ratio is the ratio of distance moved by effort to distance moved by load. That is velocity ratio. Distance moved by effort divided by distance moved by load. Now, velocity ratio is actually what makes machine a bit interesting, this topic machine a bit interesting, because almost every single machine that we are going to be looking at have a particular formula for their velocity ratio. However, what I just said just now is the comprehensive or the general definition for velocity ratio. Recall, velocity ratio is distance moved by effort divided by the distance moved by load. The most important thing I would like to talk about again is efficiency of a machine. Efficiency of a machine. I'll wipe this part so that we can see all the formulas I need to talk about the efficiency of a machine. Still on simple machine. Now we're about to continue from efficiency of a machine. Now, the efficiency of a machine is actually defined as the work output over work input times 100. That's the definition of the machine, of the efficiency of the machine. Now, when we say work output is actually the work done by the machine, while work input is the work put into the machine. So, efficiency of a machine is work output divided by work input times 100. What is work output? Work output. Let's use WOP to represent work output. Work output is actually the load the machine is lifting times the distance moved by load, work output. While work input is defined as the effort times distance moved by effort. Work output, load times distance moved by load, work input, effort and distance moved by effort. Therefore, we have the following formulas for the efficiency of the machine. One of the formula is that I can say that the efficiency of a machine is equals to WOP divided by WIP times 100. Now, another added information I would put here is efficiency of a machine is also equals to mechanical advantage divided by velocity ratio times 100. If the efficiency is given to you in percent. This is the efficiency of a machine and the formulas that you need to know. What we are going to do now is that we are going to take questions from the efficiency of a machine, mechanical advantage, before we start looking at other types of simple machine and their individual velocity ratio. All right, welcome back to class, and this is our first question on simple machine. The velocity ratio of a machine is 5. Remember I told you that velocity ratio has no unit, so this is 5. As well as mechanical advantage has no unit. So the velocity ratio of a machine is 5 and its efficiency is 75%. What effort would be needed to lift a load of 150 Newton with the machine? Now we are looking for effort. The next question is, which equation of simple machine I just gave are we going to use? Now, remember for efficiency, I told you that efficiency is work output over work input. And I told you that work output is load times distance moved by load. I told you that work input is effort times distance moved by effort. I also told you that efficiency is mechanical advantage over velocity ratio times 100. Which of them am I going to use? Since I am looking for effort, it will be wise to use efficiency of a machine is equals to mechanical advantage divided by velocity ratio. Why is this the best choice for me? Because in mechanical advantage, I have load over effort. If I can find a mechanical advantage and I already know my load, then I can make effort subject to formula. So this is the right choice for me to use. And remember, we have to multiply everything by 100. Putting in all of those values, I would say that efficiency is 75%, so this is 75, is now equals to mechanical advantage, MA, divided by velocity ratio. In a question, they told us that the velocity ratio is 5. So divided by 5 times 100. Now, it will be easier to divide this through by 100 to take this 100 over to this side. So that means I'm dividing through by 100. I will divide 75 by 100. And if I divide 75 by 100, around 0.75 is equal to MA over 5 times 100. From here, divide by 100 because we have divided both sides by 100. From here, I'll cross multiply. If I cross multiply, I'm going to have MA is equal to 0.75 times 5. Now, if we do 0.75 times 5, we are going to get 3.75. So, coming over to this side, I'm going to have MA is equals to 3.75. Now I know MA. But recall, MA is equals to load over effort. Meaning that my load, they told me, is 150 Newton, and I'm looking for effort. So 150 Newton over effort, MA is load over effort, but MA is 3.75. So I'll say 150 divided by E is equals to 3.75. Then again, I'll cross multiply. And if I do that, I would have 3.75E is equals to 150. To make E subject of formula, I have to divide both sides by 3.75. And if I do that, I'll have E to be equal to 150 divided by 3.75. If I say 150 divided by 3.75, I'm going to have 40 Newton. Therefore, the effort that I would need to raise this load 150 Newton is 40 Newton. And that falls into my initial definition that a machine is a device that enables work to be done much easily. I have to put in 40 Newton effort to be able to raise a load of 150 Newton. In the next class, we are going to be talking about other types of machines and as well as their velocity ratio. Welcome back. Now we'll be talking about types of simple machine. Number one here, we have block and tackle system of pulleys. And this diagram here represents a block and tackle system of pulley that consists of several pulleys, number 1, number 2, 3, and 4. This consists of 4 pulleys. And you should know that the velocity ratio for a block and tackle system of pulley is the number of pulleys or the number of wheels you have there. And sometimes in some exams, they will just draw the diagram like this and they can ask you questions. Now, by me just looking at this diagram, I can tell you the velocity ratio of this. The velocity ratio of this is 4. Why? Because there are 4 pulleys. 1, 2, 3, and 4. The next the next simple machine I would like to talk about is the screw jack. For the screw jack, the velocity ratio of a screw jack is 2 pi L over P, where L is the length of the turning bar and P is the pitch. If we come over to this side, you will see that this is the length of the turning bar. This is what we refer to as turning bar. And when we say the pitch, we are referring to the distance between 2 successive threads. This is a thread and this is a thread. The distance between these 2 adjacent threads or successive threads is a pitch. So when I move this guy through one revolution will mean that I hold this guy, I turn it around, I hold this end, this turning bar, I turn it around 1 revolution and come back to where I started from. That is 1 revolution. So when this move through 1 revolution, this rod here will move up or downwards by a pitch. The next is the wheel and axle. The wheel and axle is also another simple machine where the velocity ratio of a wheel and axle is the radius of wheel and divided by the radius of the axle. Now, a wheel and axle comprises of 2 wheels, a big wheel and a small wheel. The big wheel is what we call the wheel, and the small wheel is what we call the axle. The velocity ratio can also be defined as the diameter of the wheel divided by the diameter of the what? Axle. This is a wheel and axle. This big part here is the wheel, and this small part is the axle. A rope is tied around the wheel, which you can pull from this end, while a rope is tied around the axle connected to the load. With this setting, it's much more easier to pull your load than you raising it up by yourself. So this is an example of a wheel and axle. In the next slide, we'll be talking about other types of machine. Welcome back. We're going to continue from the types of simple machine that we're looking at. Number 4 is inclined plane. An inclined plane is a simple machine. And why is that so? Just like I said earlier on, a simple machine is a device that enables work to be done much easily. If I want to take a drum of oil over a certain height, it will be much easier if I put a plane that will run down so I can roll the drum up the plane. And that is what we are having here. This is an inclined plane. It's much easier for me to take a load through this inclined plane than to leave the load from here up. We also have a wedge. A wedge is an example of a simple machine. Examples of wedge will include the axe, knife. All of these are wedge because they narrow down to their sharp ends. This is a wedge. Look at this end and look at this end. If this were to be used to split a wood, if you put the wood on this end and force this guy into it, it pierces the wood, and as the wood comes into it, this slant edge pulls it apart. So it's much easier to divide a wood using a wedge than you trying to pull it apart with your hand. So a wedge is an example of a simple machine. The last one we are going to look at is the lever. Levers are simple machine. Lever simply consists of a rigid bar that is pivoted at a point where effort and load can be applied at various points. Based on where you have your lever, your fulcrum or pivot, your load, and your effort, levers can be classified into first order lever, second order lever, and third order lever. You may hear first class lever, second class lever, and third class lever. Class or order can be used interchangeably. For a first order lever, the fulcrum is in between the load and the effort. Examples of first class order lever would include first order lever or first class lever would include the scissors, the plier, even the turning bar, and a claw hammer. All of these are examples of the first order lever. The second order lever, in second order lever, the load is in between the fulcrum and the effort. An example of a second order lever would be the wheelbarrow. The wheelbarrow is a good example of the second order lever in the sense that the load is in the basin, which is in the middle. Your pivot, you have it at the tire, and then you apply your effort on the handle of the wheelbarrow. You will see that this is an example of a second order lever in the sense that the load is in between the fulcrum or the pivot and then the effort. Another example of a second order lever would be the nutcracker. The nutcracker is an example of a second order lever. We have the third order lever. In the third order lever, what is at the middle is the effort. So for third order lever, effort is at the middle, while your fulcrum and load are in between the effort. Now, these things can be confusing for a student to remember which is at the middle, which are at both sides. You can easily use this to remember for lever. Flare, 1, 2, 3. So for first class lever, we have fulcrum at the middle. What will be at the ends? Load and effort. For second order lever or second class lever, remember I told you the order or class can be used interchangeably. Load is at the middle, and what are at the other ends? Fulcrum and effort. For your third class lever, the effort is at the middle, and what are at the ends? We have the load and the fulcrum. So with this, it's much easier for you to know the orders of your lever and which are at the various positions. Now that we have looked at all of these, the next thing we have to do is to take questions using the velocity ratio. Welcome back. Still on simple machine, question number 2. A wheel and axle is used to raise a load whose weight is 800 Newton when an effort of 250 Newton is applied. If the radii of the wheel and axle are 800 millimeter and 200 millimeter respectively, the efficiency of the machine is. The question we are going to ask ourselves, which of the equation of the efficiency of the machine are we going to use? Recall, I told you that efficiency of the machine is work output over work input, all times 100. Efficiency of the machine is also mechanical advantage divided by velocity ratio times 100. Which of these am I going to choose? Well, look at the question and look at what you were given in the question. In the question, we were given the load, and in the question, we're giving the effort. What is load? 800 Newton. What is effort? 250. What can I do with load and effort? I can use to find mechanical advantage. Look further into the question. We're given the radius of the wheel, and we're also given the radius of the axle. What can I do with these two information? I can use to find velocity ratio. Because from our previous table of simple machines and their velocity ratio, we learned that the velocity ratio of a wheel and axle is equals to radius of the wheel divided by radius of the axle. So I can find velocity ratio with this information that have been given to me. So therefore, to find my efficiency, I would say efficiency is equals to mechanical advantage divided by velocity ratio. What is mechanical advantage? Mechanical advantage is equal to load over effort. And what is load? Load is 800. And what is effort? Effort is 250. If I say 800 divided by 250, I will get 3.2. No units. Why? Load is in Newton and effort is in Newton. What about velocity ratio? Velocity ratio is radius of wheel divided by radius of axle. What is radius of wheel? 800. And what is radius of axle? 200 millimeter. You may say, is it not necessary for me to convert millimeter to the SI in which it's meter? It is not necessary here. Why? Because it's a ratio of two things. In millimeter, the unit is going to cancel out. Even if you are not so sure, you are not satisfied, and you want to convert, if you convert this 200 millimeter to meters and convert 800 millimeter to meters and do this whole stuff, you get the same answer. You would have only wasted time. 800 divided by 200 will give me 4. Now, I would say efficiency, which is of course mechanical advantage over velocity ratio. We know our NA, 3.2. We know our velocity ratio, 4. Plug everything into this. I'm going to have efficiency is equal to 3.2 divided by 4 all times 100. How many times will 4 go into 3.2? 0.8 times, because 4 will go into 32 8 times. That is 3.2, is 0.8. So this will now be equal to 0.8 times 100. What is 0.8 times 100? 0.8 times 100 will give us 80%. That is the efficiency. And that's option B. Let's look at our next question. Still on simple machine, question number 3. And it goes like this. A block and tackle system of pulley has 6 pulleys. If the efficiency of the machine is 60%, determine its mechanical advantage. Now they're asking you to determine the mechanical advantage. Now, how do you find the mechanical advantage? Here they have given you efficiency. Here they have given you the number of pulleys present. From our table, recall again that for a block and tackle system of pulleys, the VR, velocity ratio, is equal to the number of pulleys. So here, our VR is equal to 6. We are looking for mechanical advantage. We are going to now use efficiency is equal to mechanical advantage divided by velocity ratio, all times 100. Plugging this in, efficiency is 60%. So we have 60 is equal to mechanical advantage, which we do not know and we are looking for, is MA. Velocity ratio is 6, all times 100. Now, divide through by 100. If I do that, I'll have 60 over 100 is equals to MA over 6. To make MA a solid formula, I'll multiply both sides by 6 to take this 6 away from here. And if I do that, I'll have MA to be equal to 60 over 100 times 6. 6 times 60 will give me 360. So mechanical advantage is equals to 360 over 100. This will cancel out this. 10 into 36 is 3.6. That is our mechanical advantage as 3.6. Option C. Let us look at our next question.